There is a natural connection between particle physics and representation theory, as first noted in the 1930s by Eugene Wigner.It links the properties of elementary particles to the structure of Lie groups and Lie algebras. According to this connection, the different quantum states of an elementary particle give rise to an irreducible representation of the Poincare group. Moreover, the properties of the various particles, including their spectra, can be related to representations of Lie algebras, corresponding to approximate symmetries of the universe. General picture. In quantum mechanics, any particular particle is written as a vector in a Hilbert space H. To help understand what types of particles can exist, it is important to classify the possibilities for H, and the properties. The particle is more precisely characterized by the associated projective Hilbert space pH. Since two vectors that differ by a scalar factor correspond to the same physical quantum state, let G be the symmetry group of the universe, that is, the set of symmetries under which the laws of physics are invariant. Starting with a particular particle in the state ket, and a symmetry transformation G in G, it is possible to apply the symmetry transformation to the particle to get a new state ket. For this picture to be consistent, it is necessary that pH holds a projective group representation of G. Therefore, any given particle is associated with a unique representation of G on a projective vector space pH. In many important cases, it can be shown that the particle is also associated with a group representation of G on the underlying space H. Wigner's theorem proves that it is a unitary representation, or possibly anti-unitary. So we conclude that each type of particle corresponds to a representation of G, and if we can classify the group representations of G, we will have much more information about the possibilities and properties of H, and hence what types of particles can exist. Poincare group. The group of translations and Lorentz transformations form the Poincare group, and this group is certainly a subgroup of G. Hence, any representation of G will in particular be a representation of the Poincare group. Representations of the Poincare group are in many cases characterized by a non-negative mass-and-a-half integer spin. This can be thought of as the reason that particles have quantized spin. Other symmetries. While the spacetime symmetries in the Poincare group are particularly easy to visualize and believe, there are also other types of symmetries, called internal symmetries. One example is color SU, an exact symmetry corresponding to the continuous interchange of the three quark colors. Approximate symmetries. Although the above symmetries are believed to be exact, other symmetries are only approximate. Hypothetical example. As an example of what an approximate symmetry means, suppose we lived inside an infinite ferromagnet, with magnetization in some particular direction. An experimentalist in this situation would find not one but two distinct types of electrons, one with spin along the direction of the magnetization, with a slightly lower energy, and one with spin anti-aligned, with a higher mass. Our usual rotational symmetry, which ordinarily connects the spin-up electron with the spin-down electron, has in this hypothetical case become only an approximate symmetry, relating different types of particles to each other. Lie algebras versus Lie groups. Many symmetries or approximate symmetries, for example the ones above, form Lie groups. Rather than study the representation theory of these Lie groups, it is often preferable to study the closely related representation theory of the corresponding Lie algebras, which are usually simpler to compute. General definition. In general, an approximate symmetry arises when there are very strong interactions that obey that symmetry, along with weaker interactions that do not. In the electron example above, the two types of electrons behave identically under the strong and weak forces, but differently under the electromagnetic force. Example: isospin symmetry. An example from the real world is isospin symmetry, and SU group corresponding to the similarity between up quarks and down quarks. This is an approximate symmetry. While up and down quarks are identical in how they interact under the strong force, they have different masses and different electroweak interactions. Mathematically, there is an abstract two-dimensional vector space, and the laws of physics are approximately invariant under applying a determinant one unitary transformation to this space. For example, would turn all up quarks in the universe into down quarks and vice versa. Some examples help clarify the possible effects of these transformations. When these unitary transformations are applied to a proton, it can be transformed into a neutron, or into a superposition of a proton and neutron, but not into any other particles. Therefore, the transformations move the proton around a two-dimensional space of quantum states. The proton and neutron are called an isospin doublet, mathematically analogous to how a spin one-half particle behaves under ordinary rotation. When these unitary transformations are applied to any of the three pions, it can change any of the pioneers into any other, but not into any non-pion particle. Therefore, the transformations move the pions around a three-dimensional space of quantum states. The pions are called an isospin triplet, mathematically analogous to how a spin-one particle behaves under ordinary rotation. These transformations have no effect at all on an electron, because it contains neither up nor down quarks. The electron is called an isospin singlet, mathematically analogous to how a spin-zero particle behaves under ordinary rotation. In general, particles form isospin multiplets, which correspond to irreducible representations of the Lie algebra SU. Particles in an isospin multiplet have very similar, but not identical masses, because the up and down quarks are very similar but not identical. Example: flavor symmetry. Isospin symmetry can be generalized to flavor symmetry, and SU group corresponding to the similarity between up quarks, down quarks, and strange quarks. This is, again, an approximate symmetry, violated by quark mass differences and electroweak interactions. In fact, it is a poorer approximation than isospin, because of the strange quark's noticeably higher mass. Nevertheless, particles can indeed be neatly divided into groups that form irreducible representations of the Lie algebra SU, as first noted by Murray Gell-Mann and independently by Yuval Ne'eman.